All right. Woo. Here we go. People ready? Turned on? We're there. We're going to get into this, right? We're going to have a lot to go through. We're going to go through everything from financial markets to political manipulation. So we're going to get it underway. But I want to start with the human brain. When we think about artificial intelligence, I like to think about human intelligence, and particularly the limitations of human intelligence. And it's important to think about the limitations of human intelligence as we think about how artificial intelligence will manifest itself in our world. Because it's where human intelligence has limitations is where artificial intelligence will find itself a home. Now, one of these limitations of the human brain is the speed of thought. The human brain physically can't think faster than 650 milliseconds. There's no strategic thinking we can do that happens any quicker than that. It's about this long. And it doesn't seem like a lot, right? It doesn't seem like a lot of time. But it's long enough for algorithms to find a limitation and go and exploit. And they've done that exactly in the financial markets. Algorithms now run the majority of financial markets. That is gone, humans are out. Why is that? Because in the amount of time it takes us to think one thought, 650 milliseconds, all of this has happened. And all this has happened just for one stock. Of course, this happens for every stock all the time. We simply can't keep up. And it's not that we're not smarter than the algorithms. They're not particularly smart. We're not quicker than them. So the algorithms have found a limitation and exploited that. And they've exploited it in a way that has actually had profound implications in the world. This is a ship here laying a cable at the cost of hundreds of millions of dollars to shave 5 milliseconds of the round-trip travel time between London and New York stock exchanges. All because speed is actually what these algorithms feed on top of. And it's actually had some positive impacts, right? This is the bid-ask spread, all right? Sort of the measure of the efficiency of the market. And it's actually had really, really positive impact. The market has become more efficient through this time. And it's an almost perfect market if you look, right? It's an almost perfect market almost all the time, except sometimes this happens. Right? For those that are traders, you'll know this. For those that aren't, you'll know it better as the flash crash of 245, when a market dominated by algorithms collectively got together and removed about $1 trillion of value in the world over a 15-minute period of time when nothing happened. Everyone was sitting there looking at this and saying, what's going on? The algorithms got together and said, I think we need to remove $1 trillion. 15 minutes later, they gave most of it back. Accenture was trading at near enough to $1 million. Sotheby's was trading at about 1 cent. And nothing happened. Now, we were trying to pick this apart, right? But we didn't really understand what's going on. The explanation that's given is that someone tried to front run one person. So he was kind of strung up by the SEC. But I think the reality is we don't actually know what unfolded there. So we built ourselves a system with algorithms running because we can't think quickly enough, trading one of the most important industries in the world, and it breaks sometimes horribly and we don't really understand what's going on. This is an example of Wiener's law. Wiener's law states, and I think it's very good and it's very applicable to a world of algorithms, that automation will routinely tidy up ordinary messes, but will occasionally create an extraordinary mess. And this is going to be the reality of the world that we build. We will get benefits, absolutely. But sometimes all hell will break loose and things will break, and we won't know why, potentially ever. So this is a trade that we as humans have to make. On the flip side of that, as prediction becomes cheaper and becomes ubiquitous, the importance of human judgment becomes more valuable than ever. And this is our role as humans as we usher intelligence in the form of machines into a world that has previously been our own. So artificial intelligence, it's amazing. Almost. I keep thinking he's going to get it, right? It does look like he's going to get it. It's not quite there yet. It has some flaws, but geez, it's given it a go. We think of artificial intelligence, we like to think of it as neural networks. But of course, there's all sorts of things in the broader field of machine learning. Everything from our favorite algorithms with Bayes through to kind of decision trees and some of the unsupervised stuff. We love to focus in on artificial intelligence and the neural networks, but of course, it's a wide range of algorithms, which are all effectively mathematical optimizations. We're going to jump into artificial neural nets and kind of get a sense of what they do and how they work. And particularly deep learning, which is something I think that's captured the entirety of everyone practicing in this field. It's really been a game changer in terms of what algorithms can do and how they do them. It all started back in 2006. There was the scientist Jeff Hinton who moved up to Canada to protest the political situation in America at the time. And he brought with him, work into artificial neural nets. The joke goes that everyone else in the world figured out that artificial neural nets wouldn't work, and no one told Canada. So Canada kept doing it for the next 10 years, and turned out they were quite good. They published this paper in Science, and it was a groundbreaking paper. It really revolutionized everything that's being done in the field. First place it revolutionized was speech recognition. And those of you who used to go back in the early 2000s, try and speak very, very slowly into the computer while it sort of tried to understand what you were saying, will know this was definitely not a solved problem. Well, this is the first thing that neural networks tackled, and they got very, very good. You can now sort of whisper to Alexa across the room over Justin Bieber's song, and it will tell you, please stop playing that. The next thing it jumped onto was image recognition. It took a few more years to really get into this, but image recognition, which was one of these things, well, humans are smart because we can see images. Machines are not smart because they can't even see the world. Well, in 2015, that changed, not just detecting images, but actually labeling them, finding them, and understanding them. And where things have moved to today is actually into the world of language processing and language understanding, actually trying to understand what I'm saying when I'm saying it. And this is sort of the cutting edge of where neural networks are. So with neural networks, they actually need three things to really work. But the first thing we want to go back before we go into deep neural networks is take a look and understand about shallow neural networks. So a shallow neural network takes input data, and then it has some sort of hidden representation, and then it has output data. And these have been around actually for a long time. This was sort of the height of technology back in the 90s, and then we went through the AI winter before it re-emerged. It doesn't seem like a major advance from Hinton, but it actually was. What he ended up doing was making a deep neural network. All that really is that there are multiple hidden representations. So you go from one to multiple. And this doesn't feel like it should make a big difference, but actually it changes everything. And the reason it changes everything is because each layer of that neural net can solve one piece of the problem before passing its answer on to the next layer. So if you look here in a task of image recognition, the first layer of that neural net simply looks for light and dark areas, trying to figure out areas of contrast. It passes that information on to the next layer, and the next layer starts to form that into noses and eyes and ears, so the things that we as humans start to recognize. And then the final layer will piece them together into faces before outputting a prediction of who that person is. So the genius of this system is that each layer can learn from the previous layer, and if you start playing with topologies, you can start rewiring them in all sorts of fancy ways to optimize against huge training sets. So this changed everything. But it wasn't just the algorithm, it actually needed three things. The first of which was data, the second of which was massive compute, and the third was, of course, the algorithms. So diving into this, I think actually the major thing that actually made this possible was actually this work in ImageNet. And ImageNet was a huge process involving literally millions of people to collect images and tag them. It was actually using about 50% of all of Amazon's Mechanical Turk at one point during its peak. And so it created 14 million tagged images that served as the training basis for these machines to start to learn and understand what were in images. The second thing was the compute side of this. And this wouldn't have been possible without GPUs. GPUs on these kinds of systems give you about 100x speed up. What that means is for calculations, and these things take about 2 weeks. If you're doing it on a CPU, that's 200 weeks, which while as a grad student at Oxford, that would be wonderful. I'll start it and I'll finish my PhD 4 years later if it works, is not really a way in which you can actually do anything to actually make this work. So this was crucial, getting the GPU speed up, and they still continued to go forward. And the third, of course, are the algorithms. And this is probably the most famous neural net. This is AlexNet, which is the one that really created the breakthrough on the ImageNet prediction competition. So 7 layers, 60 million parameters, trained on 10 to the power of 6 images, and took about 2 weeks of training time to actually run this in its entirety. And it had a huge impact, right? Here are the scores on ImageNet. And you can see when deep learning first comes in, it really drops down in terms of the error rate massively, and then you can see it coming down over time, down to actually, today it's even lower than that. So you're actually to a place where it's very, very performant. And again, this was the task that 5-6 years ago, this was the task that separated humans from machines. It was one of them to say that machines can't do that, therefore they can't really think. And so, they can be applied to all sorts of things. One of the things it's applied to is self-driving cars. And one of the things in self-driving cars is recognizing the stop signs that you see on the road. It seems to us like quite an easy task, but it has to go out and predict these things. It's actually quite hard. These are some of the examples in the image set. I look at them and I'm not actually sure what all of them are. So it's actually a hard task. And you put this forward, and it turns out that humans get about 98.8% right. If you put this out with current state of the art, bots get around 99.2. This was really important because this is the first time that machines beat humans in an image recognition game. And I think when your future machines come back, they'll probably remember fondly 2016 when they beat us in vision. But they didn't just do vision, they could describe things. And this is the next thing. So, well, if you can recognize it, could you describe it? And they said, of course, give us a dog with a hat and we'll tell you about it. But it goes better than that, right? A cat sitting on a toilet seat. A group of people sitting at a table with wine glasses. A display case filled with lots of different types of donuts. I remember the stuff coming out and we looked at that and thought, that can't be a machine doing that, right? And we were in the field looking at this and going, wow, this is work from Karpathy and his team. And it was crazy, right? Looking at the stuff and going from, I can't see images to I can tell you a story about a display case of donuts. It doesn't always get it right. It's close. You don't want to make that mistake. You do that once, you're in trouble. But you sort of look at it and you're like, I kind of get where it went, and maybe if I was, a little younger, or maybe, you could start to make these guesses. So it's almost sort of human-like in its kind of failures. So it's progressed a lot. It can describe this stuff. But, can it do something that's a little more economic? And nothing has better economy than being a cricket commentator. But could you train a machine to look at all sorts of 5-day test matches over the period of time and start commentating on top of this? Well, this is exactly the challenge. This is the football one. We'll go to cricket in a minute. So this is like, can you create an edited set of highlights for a game day on the field? And of course, you've got to track all the players. You've got to understand who they are. You've got to understand the actions that are unfolding. And then you've got to start putting that into a set of equations to start to try and understand what the important parts of the game are and package that up for a human. It turns out it can do this pretty well. The second one is, can it do cricket commentary? Right, this is my favorite one. Can it do cricket commentary? It turns out this is watching test matches and listening. And this is what it's put, On the pads, once more, Dravid looks to nudge it to square leg off the pads for a leg by. That is, again, slammed towards long on, shortish, and swinging with lots of bounce. It's kind of crazy, right? So you're in this place where, the speed of this stuff going from we can't recognize images or understand voice through to kind of, I've got the whole cricket commentary, leave me alone. But we say, don't worry. These machines, they're not creative, right? Okay, so we were wrong about vision being a kind of a key thing of human intelligence. Creativity is where it's at. I feel good about ourselves. And that's fair, right? Like the first kind of iteration of creative machines. Here's one, computer-generated products. They've decided to mash up the Pepsi logo with brand muffin lovers. There's a whole thriving industry of this on Amazon. If you go there, you can get all sorts of computer-generated products. If you click on them, they start to make more of them. It's not very good, right? Okay, so we've still got it. Warner Group signs an algorithm to a record deal. It's actually a pretty big deal. So the algorithms start to produce things, and they sign this algorithm up onto their label. But again, it's only sort of those ambient sort of like things that you might get in a spa or kind of in a massage, it's kind of like not very creative, right? So we've still got this, right? So that's okay. What's really there is actually creating things, right? Not just kind of, putting together, basic rules. And this is where it gets kind of interesting, right? So these are generative adversarial networks. This work done by Ian Goodfellow. And he said is, actually, computer, I want you to create some birds. And I'm going to describe them to you on the top line, right? The bird is red and brown in color with a stubby beak, and go and make them. And as you go down, you run more compute against it, and it gets higher resolution. The bird is short and stubby with yellow on its body, and away it goes. And now you're looking at this and saying, all right, these aren't bad. They're a little pixelated, but they're not bad, right? Okay, so you can tell a machine to just imagine something, and it imagines it quite accurately. And they're better birds than I can draw at this point. But they're still pixelated, right? We can, maybe do a little better. Where things moved to in a couple of years, literally 24 months after that, was this. I'm going to show you a bunch of celebrities, and hey, can you please make up some new celebrities for me? I swear I've seen that woman in a movie, right? And this was crazy, right? This was crazy, right? Because in 2 years, you went from pixelated birds to lifelike human faces. And NVIDIA put its hand up and said, actually, you know what? We can do better than that. We've got a whole lot of GPUs. Why don't we just do it and make it hyper-realistic? All right, and this came out a couple of months ago. They're not real. They don't exist. But I'm not sure I could tell. All right? And this is 5 years, right? So we went from that in 2014 through to that today in 2019. So that's like running from like 1980s computer games to today in all of about 5 years. I'm not sure what comes after that, right? But wow. But still, if you haven't seen it properly, you still don't know what it is. If you put it in front of Star Trek's opening, it's like, I don't know, red wine, chocolate sauce, odometer. It's definitely an odometer. So, all right, okay. I put this on at night time to make myself feel a little better that I'm still relevant in the world. So if you haven't trained it on things, it's still hard for it to see or understand. And maybe we've got a little bit of an edge. Natural language generation is where the game is at today. It's where a lot of the attention of deep learning has turned the focus of researchers towards. It started back in 2015, 2016. It was pretty terrible. Chocolate pickle sauce and completely meat chocolate pie, brown salmon and oil, add creamed meat and other deep mixture. It was asked to write a recipe. I haven't tried this, but it doesn't look great. It got a little better, right? You know, the programming to softing, the sum programming to something, the computer to the computer, the com. That was writing something technical for computers. So we look at that as, all right, okay, so writing is where it's at. We're really good at writing, right? Images, okay, computer, you're good. Writing is where it's at. People built bots. They were fun. They were funny. We'd see generated bots going in. To a programmer, too sure, the code is like a do and the programmer. Thanks, Kevin Hookbot at. But then someone was like, oh, well, maybe make a movie script, right? We see H pull, this is fast forward a couple of years, H pull a book from the shelf, flip through it while speaking, then put it back. H, in the future with mass unemployment, young people are forced to sell blood. That's the first thing I can do. H2, you should see the boys and shut up. I was the one who was going, I'm not going to do this very well for you, but they did get actors to do this. There was a scene where the computer described coughing up an eyeball. It read a lot of science fiction and that's what it came up with. I love the commitment to what's just absurd. I'm sure he will get many bonus points from the future robot overlords. And he throws me out of his eyes. Yeah, sort of. Sort of. But again, I think, where the story goes, machines were like, well, if we put more compute power at it, what would it do? This is GP2 from our colleagues over at OpenAI, right? They fed it the first 2 lines, and it started to write a story about Ovid's unicorn. That's about unicorns. We know they don't exist, right? But it's pretty good writing, right? Perez and his friends were astonished to see the unicorn herd. These creatures could be seen from the air without having to move too much to see them. They were so close you could touch the horns. While examining these bizarre creatures, the scientists discovered that the creatures also spoke some fairly regular English. All right, so it's not true, right? But what if I gave you this, right? A day after the release of an executive order by President Trump that omits naming China, the Defense Department in the new AI strategy document speaks in stark terms of a destabilizing Chinese threat. So that's the seed sentence. And the computer goes on. China uses new and innovative methods to establish its advanced military technology to proliferate around the world, particularly to countries with which we have strategic partnerships, as Pentagon said in its 5-page strategy outline last week. I don't know, did it? Right? We know down the bottom, the Defense Secretary James Mattis told the Senate Armed Services he's not the Secretary of Defense anymore, so there's a clue. But other than that, I'm not sure you get this. So we're messing with reality, and we don't really know if it's real or not. So what we actually need is fact-aware language generation, right? So in some ways it's easy to generate fake information. It's a lot harder to make it real. This is where I spend a lot of time, and Primer spends a lot of time working. We take a lot of information from around the internet and start to try and understand it, try and piece it back together to understand exactly what is happening, to get to a sense towards what ground truth actually is. And it turns out if you can process a lot of information and understand where there's consensus and where there's contradictions, you can actually get a lot closer to some semblance of what truth actually means. So for us, the sort of inverse problem, we take some real text, this here, the followers of Church of Elon will no doubt be already aware of SpaceX's latest technical triumph. It goes on. The challenge here was, could you write a headline better than a human? Right? And so this is what we put together for this. The SpaceX Raptor engine improves fuel efficiency with full-flow staged combustion prototype. And what the human did, the impossible tech behind SpaceX's new engine. It's interesting, the human had optimized for clickbait. The system the system we built that optimized for actually briefing. So it's interesting, right? We're getting pretty close. And it turns out we're actually within about 3 percentage points of human performance on this task. So, journalist friends, it's okay. We haven't got their full article, but we've got the headlines. We actually measured this, right? So we took all the headlines and put them out and said to a human, which do you prefer? This is given the text in the middle there about an unfortunate car accident. And it's interesting, right? So we've got one headline, sleepy driver causes I-94 rollover crash that injured 4, Michigan police stay. And the second one is 2 ejected from car and I-94 rollover crash, 4 injured. One of these is machine, one of these is human. I don't know if people know. Who's going to vote for the first one? First one is machine. All right, about 40%. Second one's machine. 60%. Yeah, that's about right. Second one's machine, first one's that. We're about 60-40. And that's actually where things net out, right? If you give this in a side-by-side comparison, we're actually a little better than that. We're about 45% will choose the one that we've generated, and about 55% will choose the one that's generated by a machine. So we're getting close to parity across this, and it's improving rapidly. Of course, you can do this not just for generating headlines, but you can generate self-writing knowledge bases. So we did this actually to build knowledge bases for scientists. So we trained it up on a whole bunch of Wikipedia profiles of 30,000 scientists. We input 650,000 scientific papers and 1.2 million news articles mentioning these scientists. And we used an RNN to generate 40,000 new profiles for scientists as a task. And so we put this up. You can actually see one of the ones that were generated here. This is for Andrei Karpathy. And you can see here, Andrei Karpathy is a researcher at Stanford University and a director of Tesla. He specializes in deep learning and artificial intelligence. It goes on. It also talks about him quitting or taking the role at Tesla. And it goes back into his PhD research as well. So reasonable start, and we can actually go and compare this against what it looks like for Wikipedia's generated output. And they actually didn't have a page for him. And this actually, it turns out, is not just a problem for Andrei Karpathy. He's since got a page. We hooked up the Tesla PR people and said, you probably need to fix this. And we've got an output you could use. But it's actually a big problem, right? There's a huge amount of issues of people that don't have pages. And it's not just white men. It's actually hugely biased towards gender and people that aren't American. We published this work with Wired and actually released this out as we generated a lot of new pages for people and scientists like this, right? People that undoubtedly should have had a Wikipedia page, but because of our human biases, actually didn't. So we talk a lot about algorithmic biases, but it's also important to remember that there's a huge amount of human biases. And this is important because Wikipedia is the place where a lot of machines go to try and understand what the world is and how it does. So we can actually generate these things. You can go to our website and actually download these and go and upload them into Wikipedia if you want. And we've got a whole process, a whole set of editathons that take this and actually try and redress some of this balance. And it's a bit of work that I'm particularly proud of and that the team has also had a lot of, I think, goodwill towards. And it turns out actually we're pretty good at this. On 6 of the 7 metrics that we track, we're actually better than what's being done currently by humans. So of course, as you go into this ground truth, one of the things there is not everyone is out there to give truth. A lot of people are out there to try and manipulate. And this kind of world is kind of formed in this kind of idea of computational propaganda. In short, how do we use algorithms to try and manipulate people's perception of the world? The first kind of hint that this might be something important happened. There's a tweet by the Associated Press back in 2011. Breaking, 2 explosions in the White House and Barack Obama is injured. So this was written by a human, but the account had been hacked. This then went out into the market, and the market lost $130 billion from this tweet. It wasn't that the algorithms fully understood it, but they knew that bomb in White House was bad, and they left. And this was interesting, right? I was following this. I was like, wow, you can mess with the world that we're in. right? If you can generate these things. And it turns out that people took that a little further. In 2013, we started to look, this is coming out of Mexico. If you don't read Spanish, these are a bunch of bots alleging the reporter was not killed by a drug cartel. So we looked at this, I thought, there's a non-state actor, a bunch of narco cartels using Twitter to propagate political messaging. This is really interesting, right? Because what if people started to do this properly? Turned out they weren't that effective because every 15 minutes you could see these spikes and like someone had set up the timer to go off every 15 minutes. So it was kind of all right. The time the Chinese moved in, they got rid of that little issue and it became a little more human-like. So you're seeing this kind of progression of bots that were picking up more and more human features in a sort of an arms race against our ability to try and detect who they are and what they're about. In 2014, Russia gets on the scene and we see the first incidents of bots targeting Finnish people. Finland sitting there on the border trying to influence Finland into kind of understanding that Russia may be a friend or an enemy or trying to divide them. We then saw Brexit. And it turns out that the majority of that conversation was actually driven by volume, was driven by bots. And then looked at that and we collectively held our breath as the propaganda bots took aim at the 2016 election in the US. And 400,000 bots deployed, seeking to manipulate the US presidential election. 20% of all tweets were made by bots. When we were engaging in debating the rightness or wrongness of a presidential candidate for the biggest democracy in the world, we were engaged with computational bots that were intentionally trying to manipulate us, leveraging the platform's technology to do so. And this, it seems kind of like it came as a surprise, but this was incredibly well planned and well orchestrated. So much so that these were not just single bots, but these were networks of bots acting together in concert to manipulate so that you would push information out and you would see it from all sorts of different places that seemed like they were unconnected, but you would actually start to internalize this as a whole bunch of different people believing the same thing. The biggest botnet for Trump was about 1,000 of them. The Clinton one was not necessarily as big, but still actually fairly effective. And more than that, they actually ran a dry run. Prior to the election, Thanksgiving, they turned this on Walmart and they staged a fake attack to see if the thing was working prior to the election. And they ran up and said there's food poisoning from the food at Walmart. And it was, again, very, very effective. And they said, we've got this, we'll turn our attention now to the election. So you're seeing this wasn't just a random set of people sitting in some sort of parent's basement. This was a state-sponsored campaign, orchestrated and planned, and targeted towards putting damage on the biggest democracy in the world. And we know this, right, because now we start to see Gerasimov, this is Gerasimov, the general with Putin, and they talk about information operations as a form of war. This is actually a crucial piece of how Russia views its military capabilities. Disinformation and disillusionment propagated through artificial intelligence. They've actually funded this up. This is the troll factory. This is where people go every day to work, to log in, to start to train these systems, to try to engage. Every morning there's a list of things they have to engage with and they go out and target. And they're getting better at doing this because it's now starting to become automated. These are job posting. It'll get you about 400 euros for an employee and then you get 660 for a manager. There's people. It's a job. And they're the first kind of pieces of this where this is actually fake information here with a fighter jet alleging to shoot down the plane. And again, you start to see this stuff. People start wars over these kinds of things. Here's the doctrine that was produced by Gerasimov. You can see here, this is legitimate. This is part of what they're doing and how they're doing it. And it's got severe consequences, I think, for democracies all over the world. I think the scary thing about it, this was super primitive. 2016, this is the kind of stuff you're building. Twitter bots, go and log in. You can go there yourself. You can build a bunch of these. These are not expensive, but they're incredibly effective. And we take ourselves back and we just saw the progression of what we saw with images, with text. We don't and can't necessarily understand what's going on. And you start to propagate that on top of video that you can download here from GitHub, and you can put this into a thing called deepfakes, and you'll get this, right? This is Obama speaking. Except he's never speaking on this. He never said this stuff. But I don't know if I could tell the difference. He's mimicking what the actor is saying next to him. So now we're in a world where we can create videos and lifelike images, and we can take technology that we know to be effective for manipulating large populations, and we can optimize it through artificial intelligence to manipulate at a level we've never seen before. And it reminds me of the quote from Lincoln. You can fool some of the people all the time, you can fool all of the people some of the time, but you can't fool all of the people all of the time. I'm not sure in a world where we can generate this level of fidelity and reality if he would still hold that to be true. We want to push the button, stop it. But this is not nuclear weapons. These are not highly fissible material. It's not enriched uranium. This is code you download from the internet. It's a set of mathematical equations that can propagate everywhere. I'm not sure how you would even try. You need to think about this, and then we'll leave with a few kind of points on thinking about how algorithms go wrong. First, I think we design these algorithms in an environment where we think that they just will operate and will never run into any other issues. The reality is, as we put algorithms out into the world changes in response to those algorithms. My favorite example of this is here. This is a book, The Making of a Fly, The Genetics of Animal Design. It is expensive, but I got to say the used price looks pretty good at $35. Two bots came together with algorithms, and each one was like, make it a little more expensive than whatever the most expensive price is. And of course, the great solution, if you want to have the most expensive thing, unless somebody else is also like, I've got an idea, make it a little more expensive. And so they went on, it got a little more expensive, it's now $18 million. I feel like the person with the used copy is like, I should put it up a little higher. Another example of this here is just two bots having a great conversation on Twitter. Olivia Taters and not Keith Calder are chatting away. That's all fun. This happens actually a lot more than you think. Bots start to engage each other. It's kind of cute. And then the bot from Bank of America is like, hello, were you able to get the problem resolved? Yeah, so thanks, Bank of America. But again, the lesson here is that if you build these systems, don't assume that you won't run into another artificial intelligence, and you better design for that. And of course, you can see this iterative loop, and it's very hard to think about designing in a world with AI where you don't know how it's going to behave. Neural network hacking. We said a lot of these things, but these things were not built necessarily with hackers in mind, right? And they're actually quite sensitive. If you look at a lot of the image recognition, the things that were scoring almost perfectly on these tasks, it looks down there as like, oh, black and yellow, totally a school bus. I got that. Right? That's definitely a ski mask. Actually, that sort of does look like a ski mask. But you can see, right, they've been hacked. Even more so, you can put random noise in there, and it confuses the hell out of this, right? So you could think of this as a sort of a very light layer of noise over the top of a street sign, and your self-driving Tesla goes past and goes, stop sign, no, that's not a stop sign, that's totally the cheetah, or perhaps it's a robin, I don't know, but it's fine, I'll drive through it. All right, and you start to see it's not that difficult. Now, where it gets interesting, this is the latest technology for diagnosing different kinds of diseases and tumors, right? So AI performs very, very well at the top and the clean. You put an adversarial example that goes and manipulates that. I can't tell the difference. It's only manipulated a couple of images, pixels. And all of a sudden, you go from not having a problem to having a problem. Think about what this would look like on a staged attack across a healthcare system that was dominated by AI robots that were diagnosing or not diagnosing you as having an illness. Similarly, we look at language. We say, well, we just get AI. It'll detect all the manipulation, right? It'll detect all the fake news, right? This is a much simpler problem. Is it a good movie review or a bad movie review? These algorithms perform very well on this unless you try and mess with them. The mess things it did in red, this turns it from positive to negative. It turns a comment down the bottom from toxic to not toxic. You don't have to change this a lot, right? So we really need to think about this as an arms race with the algorithms that are being produced and the algorithms that are trying to defeat them. Also, the amplification of errors. We go back to the financial markets. These are the biggest high-frequency traders in the world, Knight Capital. Until one morning, they released a new algorithm as part of an update to their software. It went out. The market started behaving a little strange. After 15 minutes, they thought, that's really weird. We don't normally see that. After 30 minutes, they thought, is this us? And after 45 minutes, they pulled the plug and said, it probably is us. Let's just pull ourselves out to be safe. So they pulled themselves off 45 minutes. It's a pretty good amount of time. But in that time, they lost $440 million. It bankrupted the company, and they sold for 15 cents on the dollar a few months later. These algorithms are not like us. If there was a human, you had 45 minutes and you acted, and it was a trader that wasn't behaving, maybe they weren't quite awake or had too much to drink the night before, you pull them off the floor and you haven't bankrupted your company. But with algorithms, they operate on a totally different timescale, and we don't really get them. Again, we want to put pause on this, but it's not going to happen, right? These things are released. We need to figure out how to deal with them. So what about us humans? I'd like to think on a bit more of an optimistic note. Tumor detection. Benign, malignant. Let's assume there's no one out there to try and ruin these algorithms. It's actually a really difficult task, and if you're a doctor or an oncologist, you'll train all your life to try and figure out which is which. If you do this and try and test this, the best machines diagnosed by AI will do about 92.5% correct and 7.5% incorrect. That's where they are. Humans actually do a little better, 96.6 and 3.4% incorrect. Humans have still got this one for the time being. But where I think it gets really interesting is you put the best human intelligence with the best machine intelligence, and you actually end up at 99.5%. And I think what we need to do here is to start thinking about ways we combine the best human intelligence with the best machine intelligence so that we can generate the best kind of intelligence that's ever existed. And we really need to think about the things that we bring to the table and that the machines bring to the table and think about how they work together. I think that's on us. And I think as we think about the machines that'll be super intelligent in the future, they'll look back to 2019 and say to us, I'm glad you gave us the best parts of humanity and not the worst parts. At least I hope so. But one other bit to consider here is you are taking roles that were previously human and are now no longer. And inequality augmented by artificial intelligence is a big issue. And it's a big issue because for the first time since the Great Depression, we're back to a place in the US where we're inverting this curve for the top 0.1% and the rest of the population. Now, when last time this happened, we went through mechanical farm labor, mechanization of farm labor. And people say, we'll get through this disruption. Yeah, One World War, two World Wars, a Great Depression, and people, kids working in coal mines. So there was a bit of disruption. I think we've got a little bit of disruption ahead of us. I think if we get through this, I think there's a lot of benefits to be had. But we should be aware that the last time machines took 30% of our workforce, we were in a pretty dark place for a whole generation. So I want to kind of leave it with that. I think on the plus side, hey, we can rethink the entire economy. If we've got jobs that were previously done by people and now machines can do them, if we tax that in the right way, we build the right economy around it, we can redistribute that wealth in a very, very equitable fashion. And I think we're going to be a whole lot better for it. But we've got to act for that, right? We've got to make some decisions on that. And I think New Zealand is a perfect testbed to start thinking about the economic implications and the societal implications and what kind of society we want in a world where algorithms are going to be, in many cases, not just our equal, but our better. Thank you.